Hello sir, my name is Manikama. Today my topic is about a bi-level control framework is proposed to improve the energy efficiency for a bi-level proposed to improve the energy efficiency for a hybrid electric tracked vehicle. The higher level discusses how to accurately predict power demand based on the Markov chain, especially fuzzy time recursive algorithm is applied to fuse power demand informative into translative probability matrix computation. Further, the Kullback labor KL divergence rate is employed to decide alteration of control strategy. The lower level computes the relevant energy management strategy. Simulation results illustrate the vehicular energy efficiency in the proposed scheme exceeds the common RL control by tuning the KL divergence value. The predicted approach and online updating expression for the power demand are from previous studies and executed in this section for mathematical completeness. First, MC based FEP for power demand prediction is introduced. Then we use a real-time recursive algorithm to fuse the power demand information into online calculation of TPMS. Finally, KL divergence rate is applied to availability of power demand prediction by comparing differences of multiple PMs. To improve the energy efficiency of a series hybrid vehicle, an optical control system is formulated in the section. The powertrain configuration of the hybrid tracked electric vehicle. The vehicle powertrain mainly includes an engine generator, a set of EGS, a battery pack, and two driving motors. The modeling of the EGS, battery pack, and cost function are first introduced. Furthermore, the RL technique framework is constructed and the Q-learning algorithm is harnessed to rapidly search the optimal control based on the online of TPM of predicted power demand. Here we can see the block diagram. This is engine, this is battery pack generated. It uses both engine and battery pack. Uh, Whenever the charging in the battery is over, it uses the engine and the fuel. The integrated part is designed. The mechanical energy is produced from both battery and the engine. Track two motors are there. To one motor to drive from the battery, one another motor to drive from the engine. Here we vehicle mass equal to 2500 kg. These are the weights according to their proportionals. Results and discussion. The proposed RL, PL and RL enabled predictive real-time energy management strategy is evaluated in this section. The influence of KL divergence rate and the fuel consumption are examined. The influence on the fuel consumption rate are examined by comparing the control performance in different threshold value cases. Then numerical tests illuminate that the energy efficiency improvement in our control strategy can exceed the common RL method by tuning the KL divergence method value A. Influence of KL divergence rate in order to evaluate the performance of the FEP for compare demand prediction. The proposed control strategy is compared with the common RL strategy in which the one step ahead predicted power demands under the two representative driving cycles are considered to improve the energy efficiency of the hybrid electric tracked vehicle. Both 90% usage of the 90 or 70 to 90% usage of battery and remaining 10 or 20% of use of engine, etc. Now you can keenly observe the diagram here. To improve the energy efficiency of a series hybrid tracked electric vehicle, an optional control problem is formulated in this section. The powertrain configuration of the hybrid tracked electric vehicle is shown. The way powertrain vehicle mainly includes an engine generator, set EGs, a battery pack, and two driving motors. The modeling of the EGs battery pack, the cost function are first introduced. Furthermore, the RL technique framework is constructed, and the Q-learning algorithm is harnessed to rapidly search the optimal control based on the online TPM of predicted power demand. The elementary parameters of the HTV power train are listed in the table. The proposed RL, PL and RL enabled predictive real-time energy management strategy is evaluated in this section. The influence of the KL divergence rate on the fuel consumption are examined by comparing the control performance in different threshold value cases. The numerical tests illuminate that the energy divergence rate in order to evaluate the performance of the FEP for compared demand prediction. The proposed control strategy is compared with the common RL control strategy in which one step ahead predicted power demands under two representatives. Here you can check the graph here. The predicted power is consumed more with speed versus time. Driving cycle A only battery. Here both battery and engine are there. That's why this compares the total amount of the load. The predicted approach and online updating expression for power demand are from previous studies and executed from the section for mathematical completeness. First, MC based FEP power demand prediction is introduced. Then we use a real-time recursive algorithm to fuse the future power demand information into online calculation of TPMS. Finally, KL divergence rate is applied to evaluate the availability of power demand prediction by comparing the differences between them. The optimal control is based both on the battery bank and the engine driving capability. Mainly, the engine is used according to the vehicle. For a car, we need a high engine capability, and for a bike, we need low engine capability. Here, two motors are used. Hence, it is mostly used for a four-wheeler. The conclusion: the main aim of the session is to how to operate the hybrid electric tracked vehicle when the battery is out of its capacity. Means when the battery is not fully charged, we can use the engine as a recursive method. Thank you.